Hey everybody, this is Mr. Beckstrom, and today we're going to talk about section 4.2. This is on the mean value theorem. And we're going to look at two different theorems. First, Rolle's theorem, which is a slightly less strict version of the mean value theorem. So the Rolle's theorem is going to lead up to our mean value theorem. And then we're also going to talk about how that kind of leads us to this idea that if two derivatives are the same, then they're only going to be different by a constant. So let's first take a look at Rolle's theorem and make sure that we understand what it's saying. So it says that f is a continuous function on a closed interval and differentiable on the open interval there with f of a equal f of b. That means the y value at a is equal to the y value at b. Then there is at least one point c in the interval a to b such that f prime of c is equal to 0. So I'm going to draw kind of a crude graph here, but hopefully it will make sense. So I have some x value a and I have some x value b. And remember, it's going to be both continuous and differentiable. Continuous means that we can't lift our pen going from a to b. And differentiable means that we don't have any sharp curves. It's all kind of smooth. And the other requirement for the Rolle's theorem is that the two y values have to be the same. So let's say this here is some, we'll call that d up here. So as long as I start here at that y value d, and my drawing just disappeared here, there it comes, and I end here at the same y value, and I have some function that's, but remember, continuous and differentiable, so some smooth curve like this. What this theorem guarantees us is that there's at least one x value in this range here such that the function evaluated at that x value is going to have a slope of 0. It's going to have a slope of 0. So let's see if we can find any places that it looks like it's going to have a slope of 0. Remember, it's at least one. That means it could be more than that. And if I just visually look at this, it looks like here at the top of this hill, I'm going to have a tangent line with a slope of 0. Here at the bottom, a tangent line with a slope of 0. It looks like maybe here I'm also going to have a tangent line with a slope of 0. So in this function here, it looks like I'm probably going to have three different places. And the way it's set up is if you look at the slope of this secant line going from AD to BD, so if you look at the slope of, change pens here, I'll pretend that those y values are the same. But if we look at the slope of that secant line going through both of those points, that's also going to have a slope of 0. A slope of 0. So this guarantees us that there's no way we can make a continuous differentiable curve from these two exact y values that would not have a point that has a tangent line with a slope of 0. All right, and the mean value theorem, let's take a look at that. I guess is a little bit different here, but it's the same kind of idea. It says that if I take some point, let's say at AD, and I take another point here at, it doesn't have to have the same y value, so we'll call that BE here, right? That if I go ahead and draw a continuous differentiable function, just something that's smooth that goes from there to there, if I take the slope of that secant line, just like I did the last time, but this time my slope of the secant line is not going to be 0. It's going to be something other than 0. It could be 0 if they were the same. It works even if they are the same. But if I take this slope here, the mean value theorem guarantees me that there's at least one place, at least one, that also has that same slope. And if you're looking here, it looks like I probably have the same slope in like 3 different places, 3 different points would have a tangent line with the same slope as the secant line with those endpoints. So that's what the mean value theorem says. Remember, this is finding the slope of the secant line, and this is the derivative evaluated at the x value of c. All right, and then the last one says if two functions have the property that the derivatives are equal for all x on an open interval I, then the difference of those two intervals is going to be equal to some constant. It might even be 0. That means that if the constant is 0, that means that the two functions that were derived from are both equal to each other. And that's going to be very important when we move on to integrals, which is going to be pretty darn soon, because we're going to have to assume that there's a constant of integration left when we find the antiderivatives. All right. So let's take a look at a couple of examples here. Okay, so for this first one, we're going to see if this function here, f of x is equal to 1 minus x to the 2/3 on the interval -1 to 1, if the Rolle's theorem applies, and if it does, what is the values of c that give you a derivative equal to 0. All right, so it has to be continuous on a closed interval and differentiable on the open interval. So the first thing I would probably do is go ahead and graph this function to look like, just to kind of visually see if it looks like it's both continuous and differentiable. All right, so going to my calculator here, go to y equals, and we're going to put in 1 minus x raised to the 2/3. And let's go ahead and graph this. And as you can see, here's -1, there's +1. It definitely looks like it's continuous, but it is highly doubtful that it is differentiable at the x value equal to 0. Why? Because it looks like that's kind of like a sharp point there, and we do not have a well-defined tangent line at that point there, which I think is 0, 1. So for some reason, it doesn't look like it's differentiable in that interval. Therefore, the Rolle's theorem would not apply. Well, let's go ahead and see why it's not differentiable at 0. So if I were to actually find the derivative of this, we're going to get negative, bring the 2/3 out front, 2/3 x raised to the -1/3. And cleaning this up a little bit, we can bring that would be -2 over x to the 1/3. X to the 1/3 is the cube root of x. And you can see that if we put a 0 in here for x, then we are going to get a 0 in the denominator, which is undefined. And that's why this thing is not differentiable at 0. Therefore, the Rolle's theorem does not apply. All right, let's take a look at another one here. All right, we have the function here, g of x is equal to x cubed minus x squared minus 5x minus 3 on the interval from -1 to 3. So go ahead, make sure this thing is continuous, differentiable, and that the f of a is equal to f of b. And if it does, I want you to find the c's that give you a derivative equal to 0. All right, go ahead and unpause when you're ready, and we'll go through the solution. All right, so first of all, this is a polynomial. Polynomials are continuous and differentiable from -infinity to +infinity, so it's definitely continuous and differentiable on this interval here. So the next thing I want to do is I want to see, let me clear this out here, I want to see if the function evaluated at -1 is equal to the function evaluated at 3. And I mean, I could plug this in manually, or I could use my trusty calculator. So if I just put this x cubed minus x squared minus 5x minus 3, I just put that in here like so. Go to my table set, make sure to put that on ask. Go to my table, and then I can evaluate this at -1 and 3, and sure enough, f of a is equal to f of b because the two y values are the same. They're both at 0. So here the Rolle's theorem does apply. So if it's continuous, differentiable, and f of a is equal to f of b, then there's at least one x value between -1 and 3 such that the function evaluated at that x value is also going to be, or is going to be 0. It's just kind of a coincidence that the two y values were 0 here. So let's go ahead and try to factor this thing here. Well, look at this. I've already put in -1 and 3, but we are guaranteed that there is at least one point in the what is that? The open interval, so not including the endpoints here. And both of those are endpoints, even though they have. Oh no! What have we done here? We haven't actually even found the derivative yet. I am a little bit tired today. Function. So find the derivative. So that's going to be equal to 3x squared minus 2x, just using the power rule, 3x squared minus 2x minus 5. And now we want to find any values between -1 and 3, which give us a derivative equal to 0. So set this equal to 0, and we're going to have 3x. So hopefully this will factor here. Is equal to 0. And let's see how we can get the minus 2. Let's see, can we do a minus 5 here and a plus 1 there? I think that will actually make it work here. Let's see. So 3x squared gives us a minus 5, and then negative 5x, positive 3x gives us our negative 2x. So this means this is going to give us two values where the where the derivative is equal to 0. So that's going to be 5/3 when I set this factor equal to 0, and then it will be -1. So let's see if both of those are in our interval. Well, the -1 is actually an endpoint, so we don't count that because we're saying inside here, but we do have the 5/3. So here we only have one value in our interval where the derivative is equal to 0, and that's at 5/3. Alright, let's take a look at a value or an example using the mean value theorem. Alright, so take a look at this one. This is f of x is equal to sine of x, and we're looking on the interval from -π/2 to +π/2. We want to make sure it is continuous, differentiable, and if it's both of those, then we want to find at least one c in the open interval. That means we're not including the endpoints here, such that the slope of the secant line is going to be equal to the derivative evaluated at that x value. So go ahead, see how far you can get, and then we will go ahead and go through the solution. All right. I'm going to go ahead and use my calculator first here. Make sure I am in radians, which I am. And let's go ahead and put this just sine x. Sine of x. All right. And make this a little bit easier, I'm going to go ahead and set my window from -π/2 to +π/2. So -π/2 to +π/2. +π/2. All right, I graph this here, and so it definitely looks like it's continuous and differentiable, and hopefully we know that the sine function and the cosine function, or sine of x and cosine of x, are continuous and differentiable from -∞ to +∞, so it's certainly on this interval here from -π/2 to π/2. So we're looking for a slope going from here to there, right? So this is going to be a positive slope because it's going from this point right there to that point right there. It's going from lower left to upper right. And then we're going to try to find at least one value in here that has the same slope as the secant line there. All right, so let's go ahead and find the slope of the secant line. So if I go to my calculator, it is going to be, so just go out here, we're going to put this in here. So this is going to be f of b minus f of a. So I'll put the entire top in parentheses here. So sine of negative pi over, the b is, we'll use b as pi over 2. So sine of pi over 2 minus sine of negative pi over 2, sine of negative pi over 2, negative pi over 2. And we're going to put that over b minus a. That's pi over 2 minus a negative pi over 2. So divided by, open parentheses, pi over 2 minus a negative pi over 2. All right, let's see what we get here. We get a secant line of this value here, and let's see how we can find, and we should actually probably do this one by hand because I'm sure we're going to get some radicals in there. So let's do that one by hand. So this is this over here. So the sine of pi over 2 is what? The sine of pi over 2 is 1 minus the sine of negative pi over 2, negative 1, all over pi over 2, pi over 2 minus a negative pi over 2. And I'm going to get, this is going to be 2 over pi over 2 plus pi over 2 is just going to be pi. So 2 divided by pi. Let me make sure that's the same value there. 2 divided by pi. We should get the same decimal approximation, which we do. So in order to find the c, what we're going to do is we're going to take the derivative of this and set it equal to the slope of the secant line here. So the derivative of this is very easy. The derivative of sine of x is just cosine of x. And then we're going to take that cosine of x and we are going to set it equal to 2 over pi. And then in order to solve this, we're going to take, I'll do it up here, the inverse cosine of both sides. So x is equal to the inverse cosine of 2 over pi. And let's figure that out. Okay, so remember, we're just looking for the interval from negative pi over 2 to pi over 2. Now, let's find out what that decimal approximation is. So if I just put a pi over 2, that's just half of pi. That's like 1.57 and negative 1.57. Let me see. Yep, so it'll be negative 1.57 to positive 1.57. Now, let's find the inverse cosine of 2 over pi. So the inverse cosine of 2 over pi, and that is going to give us 0.88. That's definitely between negative 1.57 and positive 1.57. Now, if I add 2 pi to that or subtract 2 pi to that, I'm going to be outside of that interval, so I don't need to worry about that because adding 2 pi is adding like 6.28. That's going to be way over 1.57, and subtracting 6.28 is going to be way below negative 1.57. But remember, for most of these, we're going to have two angles that will give us the same value. So we have to find that kind of the co-angle as well. And we can do that with cosine by subtracting this from 2 pi. So if I say 2 pi minus that last answer that we had, so let's put second answer, I get 5.4. Now that's outside of my range of negative 1.57 to positive 1.57. But remember, I can find the coterminal angles by subtracting 2 pi. So I can do minus 2 pi, and I get negative 0.88. And that is in my range from negative 1.57 to positive 1.57. So far I have two angles. It's going to be 0.88 and negative 0.88. So those will be my two solutions. A little bit tricky. Let me know if you have any questions on that. And that's all I got for you today. Try some of these out. And if you have any questions, let me know.